What's up everyone, welcome back to my channel. Today we're going to talk about something I personally think that is quite serious. But this actually happens mainly with the middle school students or high school students. I don't know if college students will make such kind of problem, but let's take a look at the problem first. So here we have the cubic equation, x cubed minus 1 equals 0. And of course, the question is to solve for x, but not just for real solutions. We would like to include all the solutions, including the non-real complex solutions. So if we try to use couple ways to solve it, of course, we'll get three different answers. One of them is quite obvious, which is positive 1. And again, we can just substitute back in and double check the answer. That part is not a problem. But if we look at the other two solutions here, I don't know, I have no idea why, but there are a lot of students who actually write it this way. It says 1 plus or minus square root of 3i over 2. And the problem is this correct? No, this is absolutely not correct. What should the correct answer be? Well, the correct answer should be 1 plus or minus square root of 3 times I all over 2. Now, this is the problem that a lot of students actually make, which is putting the I inside of the square roots or the radical. And they might ask, what does it matter? It's going to be the same, right? Here is the real problem. First of all, do you even understand what this symbol means? What is the square root of I? Okay, don't say that square root of I is equal to I itself. That is definitely not true at all. This is totally wrong, first of all. Okay, because first of all, we can use the definition of I to help us to find the ideas. By definition, I is what we call the imaginary unit, such that the square of I is defined to be the square root of negative 1. And as a definition, I should actually put 2 dots here. All right. So this means that if we take the square roots on both sides, we have I is now be the square root of negative 1. And in this case, we'll define it as the positive square root. And again, that is, you can think it as a definition, but that's also based on what we call the branch cut. And we say that this is a principal value. It is just similar to when we solve problems such as x squared equals 4. When we take the square roots, we should end up with 2 solutions. But if we use the symbol of radical sign, we'll keep the positive roots only, not the negative one. That is because when we use the symbol, or you can think it as an operation, we want to make sure that there is only one output coming out, meaning that there is only one answer. It has to be unique. So if there are supposed to be 2 or more answers, we need to think it as branch cut, meaning that there is a cutoff point or a cutoff line or thing, so that after the cutoff, all the other possible answers will now turn into invalid if we use the particular symbol or operation. And again, that's just pretty much saying that we need to, among all of the values, we need to choose what's so-called a principal value or one specific value as the main value that we usually would represent. So now we know that what I is. What is square root of I? In fact, if we think it as a square root of I, we now need to take the square root of negative 1. So if we try to do that, we actually see that square root of -1 cannot be the same as square root of -1. At least these two don't look the same, right? So what does that really mean? Well, it just means that we need to take the square root one more time. We need to find out what what number or what value this is, so that the square of this is equal to I, or square root of -1. How do we do it? Couple ways of doing it. We can either use complex analysis, meaning that we're going to write as a polar form, which use the Euler's identity to help us. Or if we don't know how to do it, we can just write it as regular polar form, meaning using cosine and sine. So in the last video, I've already explained that, I didn't really explain, but I've already mentioned the polar form of a complex number, which is, if we have a complex number z, we can actually define it as r times the angle, which is cosine of theta, plus I sine of theta, where theta is where r is the radius, or we can just define it as the distance of the point z from the origin, which is 0 on the complex plane. And we can just break the complex number into two parts: the real part, which is x, and the complex part, or the imaginary part, y. So r will be defined as the square root of x squared plus y squared, where the angle theta will then be the arctangent of y over x, the vertical distance over the horizontal distance, like this. Then let's see what I really means. If we try to use the definition of I is just square root of -1, but I is also known as the imaginary unit. So I, in fact, is just the same as saying 0 for the real part plus 1 for the imaginary part. So we can say that it is 0 units away horizontally, but 1 unit away from the origin vertically. Then we get that x, which is the horizontal part, is 0, and y, which is a vertical part, or the imaginary part, is 1. So in this case, we can just think this as, how should I put it? We can just think it as theta will be arctangent of y is 1, where x is 0. So technically, we can just think it as 90 degrees. But again, this is a little bit controversial, because 1 over 0 is technically infinity, but we don't have infinity. Infinity is not a number. But again, we can just define arctangent of infinity as 90 degrees. And from the plane, you can see that I is 1 unit above the origin, which is right here. So if we try to rotate from the positive x direction, or the real line, counterclockwise, we actually rotate 90 degrees, or pi over 2 radians. And that's how we get the angle here. So why does it matter? Because using the third definition of, or third way of, third expression of a complex number, we can also rewrite the expression into r, again, the radius, times e to the I theta angle. And again, this e to the I theta is telling us how much we rotate on the plane as we try to plot the point. So if we try to use this definition, here comes the result. I can be rewritten as r, and again, r is just the square root of x squared plus y squared, and we can see that the distance is just 1 unit away. So r is just 1 times e to the I theta, and again we found out that theta is pi over 2. So now we can just try to take a look what happens if we take square root on both sides. As we try to take square root on both sides of the equation, we can also rewrite the square root as 1/2 power. So the square root of I, and in this case we'll take the positive square root, meaning that we will just simply take the result from the first quadrant. That will give us e to the I pi over 2, which is what we have inside the square root. Raise it to the 1/2 power, and again that's by definition of square root. Then we can just use the exponent rule. We can multiply the two exponents together to give us e to the I times pi over 4 power. So now if we substitute back our angle pi over 4 into our second expression, we get cosine of pi over 4 plus I sine of pi over 4. So what is cosine of pi over 4, or 45 degrees? Right, square root of 2 over 2, same as a sine pi over 4. So in fact, we can write it as square root of 2 over 2 plus I times square root of 2 over 2. And that is what square root of I represent numerically. And we can see that this is definitely not the same as I itself. And graphically, we're going to get something right here, which is actually the angle is halfway between the horizontal axis and the vertical axis. And as we can see that they're not on the same ray and they're not the same points, we can say that those two cannot be the same value. Therefore, stop writing like this anymore. Don't write the I inside of the square root. It is not going to make sense for you if you don't understand it. And if you understand what it really means by square root of I, you will know that square root of I is not the same as I itself. That's it. Alright, thank you for watching. I'll see you guys in the next video.